Hello, I'm Seema and welcome to part 14 of the chapter Periodic Classification of Elements. In this video, I'm going to discuss periodic trends in physical properties. The physical property that we'll deal with in this video is atomic radii and ionic radii. What is the trend that we observe or in the periodic table when we observe these properties, that is the atomic radii? But before we talk of the trend, we must know how do we calculate these atomic radii. We know atoms are extremely small and it's not possible to find out their radii, the size of an atom directly. It's by spectroscopy that you have to find out the radius of an atom. And it's not all that simple because atoms are not present singly. They may be present as diatomic molecules, they may be present as ions, they may be present as gases, as in noble gases. So we have to keep that in mind, and when we carry out our measurements, those limitations of how they are bound or not bound also come into play when we calculate their radii. So whatever trend we observe is a general trend, but there may be a slight error in our calculations because of our limitations. But let us see what are these radii that we study. In the case of covalent compounds or covalent molecules, for example, non-metals, they form covalent bonds with themselves. You have O2, you have Cl2, you have nitrogen N2. So atoms that form diatomic molecules with themselves, if you want to find out their radius, you cannot directly find out the radius of an atom and the last shell, because the last shell is not defined and electrons may be present in a diffused form. We've studied that in quantum mechanics. So what do? If you take a diatomic molecule where it's covalently, the two atoms are covalently bound, and we have the nuclei of the two, and these two are the radii. So what will we do? We'll find the distance between the two nuclei, and if we find the distance between the two nuclei, the half of this distance should be the, sorry, I couldn't draw it exactly where it should have been. Half of this distance should give you the radius of the atom. So that is what a covalent radius is. That when you have two atoms that are covalently bound with each other, they are the same element, two atoms of the same element, we find out the distance between the two nuclei and we divide that distance by 2 to give us the radius of that element. So that is how the radii of elements which are covalently bound, which form diatomic molecules, are calculated. In the case of metals, they do not form covalent bonds. Then how do we find out their radius? Metals usually, they are present in what do we call it? Kind of a lattice. You have an entire bulk of metallic atoms which stay together, and due to the negative charge which is floating around in them, but they stay together because they form a solid. So in this solid, the distance between two nuclei of two atoms, of two metallic atoms, if you could calculate that, then half of that distance should give you the metallic radius. Now this is not the covalent radius, because in covalent radius actually there's an overlapping of the orbitals, which we ignore. But that's the only option we have. So we find out the metallic radius when we have in a metal, a solid metal, two atoms we assume are adjacent to each other and they are touching each other, and therefore we calculate the distance between their nuclei and divide it by half to get the metallic radius. So that was the metallic radii. In the case of noble gases, on the other hand, they are monoatomic, they do not combine, they are present in gaseous state, so they're not touching any other atom. The only force of attraction that is playing between the atoms of noble gases would be the van der Waals forces, which are weak forces. Now these van der Waals forces, whatever they are, the distance between two gaseous noble gases, the distance between the two nuclei and half of that would be considered the van der Waals radius. Now the problem with van der Waals radius is that it invariably has to be larger than the atom. The radius that we calculate obviously is not accurate, because it's a gas, the atoms may be close, they may be further apart, so whatever radius you're calculating cannot be very accurate. So we find that the noble gases in the end, they are usually, the radius of it is slightly larger. But that is just about how we measure these radii. Let's now come to the trend. If we go from left to right in the periodic table, we find that one electron is adding in the outermost shell. And as one electron is adding, one proton is adding in the nucleus too, because the atomic number is increasing. So as we move from left to right, one proton and one electron are adding. So as a proton increases, the nuclear charge, that is the attraction by the nucleus, increases. And as the electron increases in the same shell, because if you remember the periodic table, every period is the outermost shell. It represents that outermost shell. So as the number of proton and number of electrons increase, and protons inside the nucleus and the electron in the same shell, the distance of the shell from the nucleus is fixed. We assume it's not actually fixed, but it is, every shell has a larger radius. So if an electron is increasing in the same shell and the number of protons is increasing, the attraction by the protons, that is the positive charge of the nucleus, is increasing. At the same time, electrons are adding at the same distance. They would be attracted more by the nucleus due to an increased nuclear charge. So we find as we move from left to right in the periodic table, the size of an atom decreases. Whether the size, whatever be our way of calculating it, the covalent, metallic, we find the size to decrease. But the noble gas, because it's the van der Waals radius that we have calculated, and since it is gaseous, it does not combine, the electrons are relaxed, they're just dangling, we believe, but they're not loose to go away. So it is the van der Waals radius, so the noble gas is larger than the element before it, but otherwise the trend is that as you move from left to right, the size of an atom decreases. On the other hand, when we move in the same group from top to bottom, for example, in the alkali metals, for example, you have lithium, sodium, potassium, cesium, francium. As we go down, the period is changing and the outermost electron is adding to the next shell. So since the electron is adding to the next shell, if lithium has two shells, hydrogen has one electron in the first shell, lithium has one electron in the second shell, sodium would have one electron in the third shell, potassium, one electron in the fourth shell. So as you go down, the shell is increasing and the electron is adding, the same number of electrons in the outermost shell are adding, but the shell is the next shell. So as we go down in a group, the size of an atom increases. So we find the trend is, so what is the periodic trend in the case of atomic radii? As we move from left to right in a period, the size of an atom decreases, and as we move from top to bottom in a group, the size of an atom increases. The reason being that as we move from left to right, the electron is adding in the same shell, and at the same time the proton is adding in the nucleus. So the nuclear charge is increasing at the same distance, and it attracts the electrons closer to itself, and therefore the electrons come closer and the size of the atom decreases. But since it is the same shell, this change in size is not very dramatic. It's very slight difference in the size. But in the case of groups, as you go from top to bottom, it is one entire shell that is increasing, and the shell before it is filled. Therefore, the increase in size as we move from top to bottom is major. It's a large increase in size. So these were the periodic trends in the case of atomic radii. We now come to the ionic radius. What is ionic radius? There are two types of ions that are formed, the cation and the anion. A cation is formed when an atom loses electrons. It's positively charged. Why is it positively charged? When a neutral atom loses electrons, the number of protons remains the same. So if it loses one electron, one positive charge in the atom is more than the negative charges, and therefore it acquires a single positive charge. If an atom loses 2 electrons, then the nucleus has got 2 extra protons, and hence it becomes the entire species, that is the ion, has a charge of 2 positive. So cations are positively charged. Cations are formed by the loss of electrons, and anions, on the other hand, are when an atom gains electrons, it forms an anion. Why does it form an anion? Why is it negatively charged? Because when it gains an electron, the number of protons does not change. It remains the same in a neutral atom. But when it gains an electron, the negative charge, electron which is negatively charged, is more. So if one electron has a unit negative charge, so gaining 1 electron gives it 1 negative charge. Gaining 2 electrons gives it a 2 negative charge. Gaining 3 electrons would give it a 3 negative charge. So cations are positively charged, they are formed by the loss of electrons, and anions are negatively charged and they are formed by the gain of electrons. How does the formation of a cation or an anion affect the size of the atom? A cation is formed by the loss of electrons. Now just let us think about sodium. Sodium is a metal which loses its outermost electron in order to acquire the octet. The electronic configuration of sodium is the 11th element, is 281. It has 1 electron in its outermost shell. When it loses this electron, it forms Na positive, which has the configuration of neon. Now, which is a noble gas. So, in order to do that, it loses 1 electron, but when sodium loses that 1 electron, it is now left with only 2 shells. It had 3 shells, but with the loss of that outermost electron, it now has 1 shell less. So the size of the cation is usually smaller than the neutral atom, than the atom that it was. So sodium ion would be smaller than sodium atom because it has lost an electron. And even in the case of magnesium, let us say, if magnesium has lost only 1 electron, magnesium is 282. If it loses only 1 electron, then the configuration becomes 281. It has lost 1 electron, it has not lost a shell. But at the same time, its number of protons is the same, but the number of electrons has become less. So, the same number of protons per electron, the attraction by the nucleus experienced would be slightly more, and due to which the stronger nucleus will attract the lesser electrons towards it a little more strongly, and therefore the size of the cation would be smaller. So and usually whenever cations are formed, the outermost shell may be lost, and therefore if the outermost shell is lost, then of course the size really is smaller, as in the case of Na positive and as in the case of Mg2 positive, which loses 2 electrons and loses the outermost shell too. So a cation is usually smaller than its neutral atom, and an anion now has more electrons, but the number of protons is the same. Therefore, the effective nuclear charge, the attraction experienced by the nucleus now has 1 more electron or 2 more or 3, whatever is the gain of electrons. It has to attract those electrons too. So the total force of attraction gets distributed in the electrons, and every electron experiences slightly lesser attraction now. And then, due to that, the anion expands a little. When the attraction of the nucleus is less, the electrons can move slightly away, and therefore the size of the anion is usually larger than the neutral atom. But if you have isoelectronic species by the formation of cations or anions, for example, O2 negative, fluorine negative, sodium positive and Mg2 positive, all of these have 10 electrons. Oxygen is the 8th element. If it gains 2 electrons, it has 10 electrons. Fluorine, 9th element, gains 1 electron, 10 electrons. Sodium, 11th element, loses 1 electron, 10 electrons. Magnesium, 12th element, loses 2 electrons, again gets 10 electrons. Now all these ions whether they are cations or anions, they are isoelectronic, which means they have the same number of electrons. If they are isoelectronic species, then what will happen? The O2 negative, isoelectronic, how would you know which one is larger and which one is smaller in isoelectronic species? The size of the atom would depend on the nuclear charge, because all of them have the same number of electrons. But what is the difference between all of them? The number of protons in the nucleus. Oxygen has only 8 protons, fluorine 9, sodium 10 and magnesium 12. So which nucleus is the strongest? Magnesium is the strongest. So which will attract those 10 electrons more towards itself? Obviously magnesium. So magnesium the effective nuclear charge on the electrons of magnesium ion would be the maximum. So magnesium ion would be the smallest, while oxide ion would be the largest, although all of them have the same number of electrons. So when you have isoelectronic species, the number of electrons does not decide the size. It is the number of protons in the nucleus that decides the size of the ion. So this was about the radii. Let us now solve a problem here. The question is, which of the following species will have the largest and the smallest size? Magnesium and Mg2 positive, magnesium, Mg2 positive, aluminum, yes, aluminum and aluminum 3 positive. Which would be the largest atom and which would be the smallest atom here? Let us first see. We know magnesium and magnesium ion, aluminum and aluminum ion. Magnesium ion and aluminum ion, they have lost 2 electrons, and this is atomic number 12 and this is atomic number 13. This is the 13th element and 12th element. So we know as we move from left to right, the size of an atom decreases. So aluminum is smaller than magnesium, is clear to us. But magnesium, after forming Mg2 positive, forms Mg2 positive ion. So it has 12 protons and how many electrons? 10 electrons. And aluminum ion has 13 protons and how many electrons? It has 10 electrons too. After losing 3 electrons, it has 10 electrons. So these two are isoelectronic species. So out of magnesium and aluminum, which is larger? Magnesium is large and aluminum is small. And out of these two, cations are always smaller than the original atom. So magnesium ion would be smaller than Mg2 positive would be smaller than Mg, and aluminum, which is smaller than magnesium, would be even above this. So aluminum is here, it is even smaller, and aluminum 3 positive is even smaller than aluminum. But out of these two, Mg2 positive and Al3 positive, which one would be smaller? Obviously aluminum. So Al3 positive is the smallest atom here. So Al3 positive would be the smallest atom and magnesium would be the largest atom. So this is how we use our knowledge of the periodic trends to answer questions. Thank you for watching. If the video helped you, please like it and subscribe to my channel. Ask your friends to watch it too, and please come back for more videos in chemistry. Bye bye.